Good morning, ladies and gentlemen. It's nice to see you all. I'm glad that almost everybody is here. That's very encouraging. We are going to start with a complicated technical area, lateral torsional buckling. And I hope that you are all ready for lateral torsional buckling. I am worried because yesterday, when I came on the plane, there was a group of men from the Ukraine. This was very early in the morning, and with their breakfast, they were drinking whiskey and then vodka. So I wonder whether you as an audience have been drinking whiskey and vodka already today. I hope you have not, because lateral torsional buckling is a complicated subject. So this is lateral torsional buckling. This is an effect that we need to consider if there is no restraint to the compression flange. We are on page 107 of your workbook. So this beam has been drawn in the conventional sense. We have compression on the top flange and tension on the bottom flange. And the compression flange wishes to buckle. It cannot buckle in the vertical direction, so we'll wish to buckle in a lateral direction. The tension flange is just like a piece of string and wants to remain exactly where it is. So the tension flange wishes to remain in a straight line. This is another view of lateral torsional buckling. So here is the unloaded beam. Here is a beam with a vertical load on, so a compression flange is the top flange, the tension flange is the bottom flange. The top flange wishes to buckle laterally, the tension flange wants to stay exactly where it is. It's simply in tension. And therefore you get a lateral movement and you also get a torsional movement, which gives rise to the name lateral torsional buckling. In a very simple way, there is a compressive stress in the top flange just due to the major axis bending. So that stress might be bending moment divided by modulus. And then because the top flange is moving laterally, there is another bending stress in the top flange. So when you combine these two stresses and they reach yield, then you've got the potential for lateral torsional buckling. That's a very simple description of the effect that we're considering. So there are three ways to deal with lateral torsional buckling in the Eurocode. There is the general method. And in the United Kingdom, we would say that the general method will be used by researchers only. We do not have any confidence in the general method. You would need some very clever software to use the general method. And certainly in the UK, we generally guide people not to use the general method because people have not access to the software and they are very unfamiliar with the method. There is a very simple method, and I tried to introduce the simple method yesterday by saying that a beam, when it is bent, has a top flange that thinks it's a strut. So the general method is to identify the top flange plus a third of the compressed length of the web. And just imagine that that's a strut. And like we did yesterday afternoon, just determine the resistance of a strut under compression. That's a very conservative approach because you are throwing away the benefit of the tension flange, which wishes to stop this compression flange buckling, and you're also throwing away or neglecting any torsional resistance that this member has. So to design this member simply as a strut will always be conservative. The recommendation would be to use the buckling curves. That's what we will look at today. So perhaps in your workbook, no, in your guide, you could look at page 52 at the same time. So yesterday, when we were thinking about compression, you will remember that the resistance was a reduction factor chi multiplied by area multiplied by yield divided by gamma m1. Now we are in bending, lateral torsional bending, so the reduction factor now has the subscript LT, which stands for lateral torsional bending. So everything connected with lateral torsional bending has a subscript LT. So the imperfection factor alpha is now alpha LT. And the intermediate term phi is now phi LT. So everything in the family is to do with LT. I think that's good, because if you were to ask me a question and to say, how do we identify alpha LT? I know that you're thinking about lateral torsional buckling. If you said, how do I identify the factor alpha? I know that you're thinking about buckling under pure compression. So to me, the Eurocode system is good. Notice that the modulus is described as WY. And then you must decide which modulus you're going to use. And the modulus to use, of course, depends on the classification. So yesterday we classified a member. And it was so that we know it's class 1 or class 2 or class 3 or class 4. For class 1 and 2 we would use the plastic modulus. For class 3 we would use the elastic modulus. So, again, like yesterday, we must calculate the reduction factor chi LT. There are two ways in which we can calculate chi LT. The first way is called the general case, and it is the general case that you will see on page 52 of your guide. The formula halfway down page 52 can be used for any section. It's a conservative approach. There is another set of formula which you do not have in your workbook, but I will show you, and they are for use with rolled sections or equivalent welded sections. So my background is with rolled sections. So I will always be using the special case for rolled sections, because that will give me some advantage. If you use the expressions on page 52, they are perfectly fine, but they may be a little bit conservative compared to the special case for rolled sections. If you look at the formula on page 52, you should recognize the formula because they are the same as we saw yesterday for compression. That's appropriate because lateral torsional buckling can be considered, as shown on the flip chart, as a strut under compression. So perhaps we are not surprised that the formula look precisely the same. So those are the formula, and you will see those on page 52 of your guide. It's expressed in precisely the same way we have this intermediate term to determine, phi LT. Phi LT demands that we know alpha LT, just like yesterday, an imperfection factor. And we need to know this slenderness, now called lambda bar LT. The imperfection factor alpha LT comes from the table at the top of page 53 of your guide. So there is a simple test depending on the H over B ratio. Is it smaller than 2 or is it larger than 2? Then we would extract the imperfection factor from the table at the bottom of page 52, and then we can start to calculate the intermediate value phi LT. Now, of course, instead of the calculations, you could use the lookup table on page 55 of your guide. So who would ever want to do the maths? Me. I would like to do the maths. But for convenience, you could use the lookup table on page 55. Our final challenge is that we must determine the slenderness lambda bar LT. And again from yesterday, when we were dealing with compression, you will remember that the expression for the slenderness lambda was the root of area times yield divided by n crit. And I called n crit the Euler load yesterday. Now we are in bending, but the expression is presented in the same way. The root of modulus, notice that the modulus is wy. So again, we must decide which modulus to use, and that modulus will depend on the classification. So our examination of classification yesterday was very important. The yield strength that we use, the same rule will apply as we applied yesterday. The yield strength is based on the thickness of the thickest part of the section. So in my world, which is rolled sections, the yield strength would be based on the thickness of the flange. And then instead of n crit, the Euler load yesterday, we now have m crit. Now, in the UK, when we first opened the Eurocode and we found this term m crit, nobody in the UK had any idea about what it was. We had never met m crit ever. It was never part of our education. So for us in the UK, and maybe you, we must turn to some other source of advice, because the Eurocode does not tell you how to calculate m crit. It's one of those things which some countries think is to be understood by graduates. They think it's part of their education. So I have two options for you, ladies and gentlemen. The first option is that you could use some free software. And there are a number of software programs which are available. The one I use is called LTB, all one word, LTB. So you could Google LTB. You could go to this website, which is the website for the French Steel Construction Institute. You would go to their site, and again you would search for LTB, all one word. I will probably demonstrate LTB to you later on. Once you have installed LTB, and that might be a problem because you have to install it in French and then change the language. You can open a catalogue and you will find European sections, you will find universal beams, you will find the opportunity to describe members by dimensions. So if you are designing a member fabricated from plate, you can enter the width and the height and the thickness of the plates. You would then enter some loading, so there is opportunity to put moments, there is opportunity to put concentrated loads, or there is opportunity to put uniformly distributed loads. And the reason why you enter the loads, is that you want the shape of the bending moment diagram to be correct. Because M crit is influenced by the shape of the bending moment diagram. So one of the important themes for me this morning is that you must be concerned about the shape of the bending moment diagram. The overall value of the bending moment diagram does not matter, but the shape of the bending moment diagram is of critical importance. That's why in the software we enter the loads to get the right shape of the bending moment diagram. And then we continue and we ask for the software to determine M crit, and the software does some very clever things and tells us that the M crit value in this case is 162. And just like yesterday, you perhaps need the microphone. The microphone is on the way.
One question, share diagrams. Share diagrams.
I'll need it translated. Hang on.
Мой вопрос. На балку действует распределенная нагрузка?
Could you say again?
Распределенная нагрузка действует на балку. Скачок, почему?
Yes, it is. Yes, because for a distributed load, you have a parabolic bending moment diagram. For a point load, you would have straight line bending moment diagram.
Ну, предыдущий слайд, там была схема распределенная нагрузка, силы не было.
Есть, была.
Вот. Распределенная нагрузка, сосредоточенной силы нету на этой схеме.
Они так обозначают,
Мы просто не так.
Okay, here, ladies and gentlemen, here on this screen, we have a distributed load and we have a point load. But the point load is very small, so it does not have much effect on the bending moment diagram. The bending moment diagram, in this case, is dominated by the uniformly distributed load. Does that answer your question, sir? Okay. So we press the software button, we get an answer which in this case is 162 kilonewton meters, and in the UK we have no idea whether this value is correct, because we do not recognize the term. It could be 100 difference, it could be 1,000 difference, but in the UK we have little experience to be able to say whether this is correct or whether it is incorrect. However, I would reassure you that if you use the software correctly, you get a precise answer. So I would recommend this software to you. The reason why people perhaps prefer the software is that they do not like the formula. This is the most general formula. This formula allows you to deal with, the diagram on the right here shows a destabilizing load. A destabilizing load is a load which is free to move as the compression flange buckles. And as you can see, if the load is free to move, then the load is now eccentric to the shear center, so there is an additional moment trying to buckle this beam. So destabilizing loads are very bad. Many times we do not have a destabilizing load because perhaps there is some form of flaw on the top flange and the load cannot move with the top flange. But engineers who design supports for equipment or for industrial plant, and maybe the entire piece of equipment can move with the beams as the beams buckle, then that will be a destabilizing load. Because the basic assumption is that the load is applied at the shear center. And we will look later on and we will appreciate that if you have assumed that the load is applied at the shear center, but you really have a destabilizing load, that will be very detrimental for the resistance of the beam. So in these formula, you will notice the term ZG, ZG. And the dimension ZG is from the shear center to where the load is applied. So perhaps the load is applied at the top flange. Perhaps if you have equipment supports, the load is applied even above the top flange, which will make the situation even worse. If you have the load applied below the shear center, then that's described as a stabilizing load. Because here, if the load was applied to the bottom flange in this case, then there is a restoring moment applied to this beam, and that will improve the resistance of the beam. So a second theme for me this morning, ladies and gentlemen, is to alert you to the concern about destabilizing loads. If you look on page 53, you have an expression there for M-crit, halfway down the page on page 53. And that would be the expression which is used most of the time, because we do not have to allow for destabilizing loads. So the expression on page 53 assumes that the load is applied at the shear center. And that will be the common situation. And you can see that it is a simple form of the general expression. If you look at the formula on page 53, you will see the term IT. Capital I, subscript T. that's the torsional inertia. You will also see the term IW. That's the warping inertia. In my world, those two terms are easy because they are found in lookup tables. But if you are designing a plate girder or a member fabricated from pieces of plate, you will need to calculate those. So I recommend that you use Excel. You will also see on page 53 that the expression starts with a variable C1, capital C subscript 1. And that variable, C1, deals with the shape of the bending moment diagram. So in the software, it was very important that we put the correct arrangement of loads to give the correct shape of bending moment diagram. In the formula, it is also important that we allow for the shape of the bending moment diagram. And we allow for the shape using the C1 variable. The Eurocode does not tell you how to determine C1. So you would turn to page 54, and at the bottom of page 54 you will find some details for different shapes of bending moment diagram. You will find values of C1. So at the bottom of page 54 there are diagrams for the very common bending moment diagrams. So for a uniformly distributed load, for a central point load, and I would imagine that that will cover 90% of the beams that you design. So there is the expression that you saw on page 53. That would be the expression to use when loads are not destabilizing. Although this expression does not look very nice, it is quite straightforward. All of these are section properties or they are constants. So again, I would recommend that you use Excel. So for you today, I have written some Excel. So I can enter a member fabricated from steel plate, and I can calculate the section properties, because we are going to need those a little bit later on when we do a worked example. If you don't want to write your own Excel spreadsheet, then I would remind you that you can use LT Beam. There are other programs available, and you can create members simply by specifying the dimensions. And then the software will calculate all the section properties for you. Final reminder from me, the shape of the bending moment diagram is very, very important. Do I need to listen?
Скажите, пожалуйста, C1, если есть поперечная сила плюс распределенная нагрузка, какой будет коэффициент? Тут есть отдельно для силы, отдельно для нагрузки распределенной. Да, если они одновременно, вот как в том примере, как раз, кстати.
Okay, when you mentioned a lateral force, do you mean a concentrated force, or do you mean a lateral force?
Да, я имела в виду нагрузку, да, конечно, да.
A concentrated force. Okay. The C1 factor relates not to the bending moment diagram for any one load, but the bending moment diagram overall. So the question is usually, if I have a very unorthodox arrangement of loads, so the bending moment diagram looks unorthodox, what do you then do? And the answer is that you should choose a small value of C1. So you are more conservative if you choose a lower value of C1. The most conservative that you could be is to choose a C1 value of 1. 1. Most conservative. So if you really did not know what to do, then you would always be safe to choose 1.0. In some circumstances, to choose 1.0 will be very conservative. And if you worked for a steelwork contractor, you would be uneconomic. If you would like to look again at page 54, if you look at a uniformly distributed load, you will see that the value of C1 is 1.13. On the right-hand side of the table, at the bottom, for a uniformly distributed load and a parabolic bending moment diagram. I hope that you can see 1.13. 1.13 is only a little bit larger than 1. So if you had a uniformly distributed load, you would not be being very conservative simply to use 1. However, if you look at the straight line bending moment diagrams, you will see that if you had a reversing bending moment diagram, then C1 might be as large as 2.76. In those circumstances, if you chose a C1 value of 1, you would be being very conservative. And if you worked for me as a steelwork fabricator, I would have to ask you to leave, because you would be being very uneconomic. Okay. So, the software gives you the value of mcrit. The equations give you the value of mcrit, and both the software and the equations give you precisely the same value as of mcrit. If you wish to calculate C1, then you could use the software and you could calculate mcrit for the actual bending moment diagram. So if you had a very complicated arrangement of loads and a very unusual bending moment diagram, then you could use software to calculate mcrit. And then if you divide by mcrit for a uniform bending moment diagram, and please note, ladies and gentlemen, this is not a uniformly distributed load. This is a uniform bending moment diagram. So typically it would be a beam with end moments on to give you a uniform bending moment diagram, not a uniformly distributed load. And if you divide one by the other, that will give you the value of C1. You could take the value of C1 and, using the expression on page 53, you could then calculate mcrit. But why would you want to do that? Because you've calculated mcrit using the software. You can calculate mcrit using the software, or you can calculate mcrit using the formula. So here was one small example that I tried. You can see the values. One is for a uniform bending moment diagram. The value of mcrit is 871. The value for a uniformly distributed load is 985. Divide one by the other, and the answer is 1.13. So you can calculate it if you want to, but of course for a uniform bending moment diagram, we know the value is 1.13 to 2 decimal places. So the process, ladies and gentlemen, is to calculate the slenderness first of all. And to calculate the slenderness, you need to calculate mcrit. And today, you do not have the software, so today you will need to use the formula on page 53. Once you have calculated mcrit, then you can calculate the slenderness. Once you have the slenderness, you can choose a curve, and you would choose a curve from the table at the top of page 53. If you have the slenderness and you've chosen the curve, then you can choose to be mathematical and use the formula on page 52, or you could use the lookup table on page 55, and that will give you the reduction factor chi-LT. Once you have chi-LT, you would look back at the expression at the top of page 52 and say the resistance to lateral torsional buckling is chi-LT multiplied by the modulus multiplied by the yield strength divided by gamma M1. So, ladies and gentlemen, immediately following page 118, there is the first of, in fact, 3 worked examples. I would only like you to do the first one for the moment. So there is a member fabricated from plate. It has a length of 6 meters. I have classified the section for you, and I have found that the section is class 1. So that means wherever you see the modulus WY, you should be using the plastic modulus. And you'll see, as part of the data, I've given you the plastic modulus. I've used some software and I have calculated the section properties for you. So you have the torsional inertia, you have the warping inertia, you have the constants G and E, and a little reminder there of the formula for mcrit. The load is a uniformly distributed load, so I hope that you will use the values on page 54 to remind you that for a uniformly distributed load, there is a certain value of C1. You will need that for the calculation. So you calculate mcrit. You turn over the page, I hope, and then you will calculate lambda bar LT. You will choose a curve And then perhaps you will use the lookup table to determine chi LT. And then you'll calculate the resistance. So I guess it's only going to take a few minutes. In the UK, this example goes badly wrong because people use incompatible units. They choose millimeters for one term and centimeters for another term. That will not work. So however you rearrange these units, please use compatible units in your calculation. So for a uniformly distributed load, C1 is 1.13. And then it's simply a matter of substituting 1.13, all the section property which was given you, and I believe the answer is 993 kilonewton meters. Did anybody else get 993 kilonewton meters? Excellent, well done, gentlemen. Here is LT beam. So here is the very same section. It's 450 millimeters deep. It has a 10 mil web. It is 250 millimeters wide, and the flange is 20 millimeters. So I have defined the section in LT beam. I have put on a uniformly distributed load. It does not matter the value that I have used, because it's only the shape of the bending moment diagram which is important. And here you can see the parabola, which is the shape of the bending moment diagram for a uniformly distributed load. And then the software calculates the value, and the software says the value of mcrit is 985. And using the formula, I got 993.6. The difference to me is trivial. I do not care that there is a difference. I think it is less than 0.5%. And the difference is probably because within these values there are some significant figures instead of using very many decimal places. In this value, 1.13, we have only used 2 decimal places, and maybe if we'd used some more, then we would get precisely the same answer. So the difference is small enough to be ignored. Then we can calculate lambda bar LT. We need to know which modulus to use. The section is a class 1 section, so we must use the plastic modulus. We need to know the design strength to be used. And because the flange is 20 millimeters, it's thicker than 16 millimeters, and therefore we use a reduced design strength of 225 newtons per square millimeter. So I calculate lambda bar LT 0.763. And then I think you could have used the lookup table, because you would choose curve C, I believe. You could then use the lookup table, or if you work in the Steel Construction Institute in the UK, you enjoy the maths. So I have continued to do the maths. And I calculate the reduction factor to be 0.685, and I think the buckling resistance is 396. So, ladies and gentlemen, did you calculate somewhere near 396? Close? Did anybody else get anywhere near 396? Excellent. 2 out of 80 people. What? 3 out of 80 people. Well done. Please, could you make a note of M crit? Whether you calculated M crit or not, please make a note of M crit 993 kilonewton meters, because we will need that in the next exercise. Please also make a note of the final answer, which was, in this case, 396 kilonewton meters. You have been using the general case. You can always use the general case. It may be a little bit conservative. I want to go and show you now the special case for rolled sections and equivalent welded sections. Now, you do not have this in your notes because the extracts that I provided for your notes were not included in your pack. So I would ask you to look at the Eurocode. I am sorry that it is in English, but I'm sure that you will recognize the formula. So the clause at the top says this is the special case now for rolled sections and equivalent welded sections. And you will look at the formula and you will say, I recognize those formula because they look almost the same as the ones I have just been using. But there are 2 differences. First of all, there is a variable beta, which is appearing twice in the expressions. Beta has a recommended value of 0.75, and the Ukraine National Annex accepts that value of 0.75. It also has another term, lambda bar LT0. So if you look back at the previous formula, that value was 0.2. In this special case, it's described as lambda bar LT0. It has a recommended value, and the value is 0.4. The Ukraine National Annex accepts that recommended value of 0.4. The variable lambda bar LT0 is the length of the plateau before there is any reduction taking place. So in this special case, the length of the plateau goes out to 0.4. In the general case, you will recall that the plateau is 0.2, and then we start to get a reduction. And that shows you in graphical terms why the special case is going to give you a slightly better answer. We have a longer plateau before we start to reduce, and we have a different curve because of the influence of beta being 0.75. So for me, back in the UK, because I am always using rolled sections, I would be advising UK designers always to use these expressions because they give a slightly improved answer. I do not have any problem if you continue to use the general case. The general case is always safe. So, this slide covers the special case, and it's a reminder of the things that I have said. A slightly different expression with lambda bar, LT0 and beta, with recommended values for those two variables, and the Ukraine National Annex accepts the recommended values. You must choose your curve from a different table if you use the special case, but for welded sections, which is what we are considering today, the choice of curve is exactly the same. So maybe no difference there. The final difference is that the special case allows you a little extra modification. And here it is. We calculate a modified value of KLT, and the modified value is KLT divided by a variable f. So this is getting involved and complicated, and you may think, I don't want this extra complication. I'm happy to stick with the general case. If you were working for a steelwork fabricator where every kilogram is important and you wish to produce the lightest possible structure, then you would use the special case and you would appeal to this modifying factor f. As you look at the modifying factor, it depends on lambda bar LT. We've already calculated lambda bar LT. It also depends on a variable KC. And the Eurocode says you determine KC from table 6.6 of the Eurocode. You don't have today access, unless you've got the Eurocode on your laptop, you don't have access to table 6.6, but here it is. So we look in table 6.6 for the situation that we are considering, which was a uniformly distributed load, which produces a parabolic bending moment diagram, then KC is 0.94. If the shape of bending moment diagram is not covered by this table, then there is a relationship between KC and C1, and you see that over on the left-hand side. So there are alternatives available for you, ladies and gentlemen. You could use the general method, but I would remind you I suggested that is for researchers primarily. You could use the simplified method, where we identify the top flange as a strut acting in isolation, and that would be very conservative. So I do not recommend either of those two alternatives. I do recommend that you use the buckling curves, and then again you have two choices. You could either use the general case, and the general case is the one which is described in this guide. Or if you wanted to undertake additional effort and demonstrate a slightly increased resistance, then you could use the special case for rolled sections. A little bit of advice is that when C1 is 1, the additional benefit you can derive by calculating the modified value. So the additional benefit by calculating KLT mod does not exist if C1 is 1. If C1 is 1.13, so quite close to 1, then you do not get much benefit. If you have, for example, a reversing bending moment, when C1 might be as large as 2 or 2.5 or 2.7, then this modification due to F will be very beneficial. So, in my world, I would always be using the special case, and I would be appealing to this modification factor. So, ladies and gentlemen, I would like you to attempt the second worked example, please. And this is just to examine the use of the special case. And you will see the title is called LTB Resistance 2. It is exactly the same beam, so with the same data. And I hope you made a note that the M crit value is 993. In fact, it's on my sheet here. There is no need to recalculate the slenderness, lambda bar LT, it's exactly the same. So the only difference comes in the formula down at the bottom of the page. Remember that lambda bar LT0 is 0.4 and beta is 0.75. So perhaps if you could carry out the calculations to determine pi LT and then turn the page and determine the modification factor F, then we will be able to see what difference going from the general case to the special case makes. And you will be able to decide whether it is worthwhile using the special case. This should only take a few minutes, ladies and gentlemen. So I calculate the revised reduction factor chi LT as 0.787. It has changed because now we have lambda bar LT0 as 0.4 and we have beta appearing in the formula. Beta is 0.75 and it appears twice. So we calculate a revised value of chi LT. And then we appeal to this further modification by the F factor. The F factor demands lambda bar LT, which we have already calculated. And we also need the variable Kc. And Kc for a uniformly distributed load is 0.94. So we determine the result of the expression, and the result of the expression is 0.97. So the modified value is 0.787 divided by 0.97. And that's why I said to you earlier, if C1 is small, then the value of the modification is trivial. To divide something by 0.97 is almost worthless. We continue, we calculate the buckling resistance, so the reduction factor, this is the modified value now, chi LT mod, multiplied by modulus, multiplied by design strength, gives 469 kilonewton meters. Did anybody calculate anywhere near? Excellent, excellent. Oh, good. Okay. So the question for you, ladies and gentlemen, is the difference between the general case and the special case, is it worthwhile? Of course, I would say it's very worthwhile. If I worked for a steelwork contractor and I was throwing away that sort of resistance, I would go out of business. My last comment to you was that when C1 is small, the modification in the special case is not very worthwhile. We saw in that particular example that F was calculated at 0.97, so not significant at all. Here is the same example, but now the bending moment diagram on the beam is triangular. So the bending moment diagram on the beam looks like that. So in your guide, if you look on page 54, for the straight line bending moment diagram, you'll see that you need to calculate psi, the ratio of the smaller bending moment diagram divided by the larger bending moment. In this case, we have 0 divided by something. So the answer is 0. And if you look on the right-hand side of this table, you will see that the C1 value for a triangular bending moment diagram is 1.77. So significantly higher than 1. I calculate a new value of M crit. It's the same beam, but remember C1 enters the expression. So I have a new value of M crit. If I use the general case, so that was the first example that you completed this morning, the buckling resistance moment would be 451 kilonewton meters. If I use the special case, then the modifying factor is now quite attractive. Instead of dividing by 0.97, which was almost worthless, we're now dividing by a small number, and that is worthwhile. And then you'll see if you use the special case, the resistance here is 573 kilonewton meters. So quite a difference between the two cases. So what do we understand? We understand that when C1 is 1, then this modification factor has no effect at all. When C1 is small, it has only a trivial effect. But when C1 grows larger, then there is value in this modifying factor. And the second thing we observe is that you will get an increased resistance by using the special case, but the general case can be used in all situations and is always slightly conservative. Now, I am not going to ask you to complete the third example. You will get a completed worked example at the end of the day. But I would just like to, on the flip chart, add the final value here. So if you have destabilizing loads, ladies and gentlemen, and you calculate the resistance using the general method, so really we're comparing the general method in both of those two situations, then the resistance is reduced to 346 kilonewton meters. So you must be careful. If you have assumed in your design that loads are not destabilizing, and therefore you've calculated a resistance of 396 for your beam, and perhaps that is okay. If in reality you have destabilizing loads, then the resistance can be significantly lower. And I tell you that just to make you aware and maybe make you concerned about the possible danger of destabilizing loads. For those of you who design plants or equipment support structures, it's probably likely that you find destabilizing loads. If you are in building construction, maybe you do not find destabilizing loads. I'd finally just like to show you LT beam again. So this is LT beam again. This is the same example that we saw earlier on. LT beam allows us to very easily calculate mcrit for destabilizing loads. Because if you did look at example 3, you would see that the formula is very, very complicated. If you're going to do the formula more than once, then I would very strongly recommend that you use an Excel spreadsheet. But the free software allows you to introduce destabilizing loads and allows you to introduce the dimension, in this case, above the shear center where the loads are applied. And now in this diagram on the right-hand side here, you can see that the loads, perhaps not very clearly, but they're now applied above the level of the beam. And that will allow you to introduce destabilizing loads. You can then simply calculate a new value of mcrit. So if you want an easy way to calculate mcrit, then there are a number of software programs available for you. There will be plenty of software available for you to design beams. If you wish, you could write an Excel spreadsheet. Here is the example that we have been examining this morning. You can see it's relatively easy to calculate the resistance moments for the general case, and easy to calculate the resistance moment for the special case. I've calculated this adjustment factor F that we did in example number 2, and these are the resistances in compression that you calculated yesterday afternoon. And of course, it's easy to change to a different shape of bending moment diagram. So to me, if you are going to design beams regularly, and you are going to define plate girders regularly, then I would recommend that perhaps you use LT beam software, or perhaps you develop your own spreadsheet. I had some questions about destabilizing loads, so I would like to try and explain destabilizing loads again. This is a cross-section of a beam. It has no restraint to the top flange, so the top flange is free to buckle. We apply some vertical load. There is no lateral load on this beam, there is only vertical load. There is no bending moment applied to this beam, there is only vertical load. But because of the vertical load, the top flange experiences compression and the bottom flange experiences tension. So the top flange wishes to buckle, and eventually it will buckle laterally. If the load can move with the top flange, so if the load can also move laterally, if it's free to move, then that is a destabilizing load. There is no lateral load. This is an effect under vertical load only. And the problem is that we are now eccentric to the shear center, and that wishes to add a further contribution to lateral buckling, so that makes the situation even worse. I hope that's a better explanation of destabilizing loads.